This is the PC Train AP1000. PC Train is a nuclear power plant simulator, and AP1000 is the Generation 3 advanced PWR developed by the Westinghouse Electric Company. There are two Plant 4 units in construction in China, and two more Plants 4 units in the USA. PWR here are the control assemblies, and the red vertical assemblies symbolize fuels. Hot water is pumped through the core going to the hot leg, and the steam generator inverted U-tube return to the core downcomer. That's just like any other PWR. Steam is generated in the steam generator and goes into the steam turbine and the generator. Steam is condensed by the condenser and pumped back into a steam generator feedwater line. And pressurizer, the chemical and volume control system, control the pressure and the level and the boron concentration. That's just like any other PWR. And control could be either by the control rod. In PC Train, we use point kinetics, so the reactivity of the rods converted into percentage of withdrawn. So inserting the rods, the power will go down. There are also very sophisticated systems to control the pressure, water level, feed water, and turbine pressure, such that the reactor is under control, just like an autopilot of an airplane. And to do common normal operation, suppose we reduce the power to 80%, controlled by the turbine, and we can start a run, and you see the rods will slowly inserted into the core. In order to accelerate that, we can see the more visible. PC Train allow us to do fast time. Now we're doing 4 times faster. See the rods going in and the power go down. In the meantime, the spray or the heaters are working to maintain the pressure, primary pressure, as close to the original 2250 psi as possible. And we can see the operating variable curves, transient plots, and the variables are in alphabetical order. I can click the power of the core thermal and neutron flux and the turbine power in percent of nominal. So far we run 200 seconds. Suppose I type here 600 for the time span seconds. You see the power, turbine power go down 10% per minute. So in 2 minutes down to 80%. The neutron flux and the thermal power follow that by the control system. So pretty soon we will reach a new equilibrium of 80% power, and then we can raise the power back. Okay, that's just like any other PWR. And I can check the pressure of the reactor, primary and secondary side, steam generator, from 0 to suppose to 3000, and okay. You see the reactor is controlled very stable. Primary pressure about 2200, and secondary, the steam generator pressure actually go up, according to the design to maintain stable operation. And what's unique for AP1000 is it do away with emergency diesel generator for AC power supply after a loss of offsite power accident. It uses natural circulation and passive concept to remove the decay heat. Using this opportunity, we just continue to operating at 80% power. We choose control and more function, and there are 20 categories of accidents or malfunction. Loss of coolant accident, hot leg, cold leg, steam line break, loss of flow or lock rotor, turbine trip, steam generator tube rupture, moderated dilution, containment failure. So everything feasible in a power plant are included. They are not mutually exclusive. You can have one accident on top of another. So suppose we have a cold leg, medium size of brake, say 300 centimeter square. Activate, OK, and close. Suppose I use fast time will miss the highlight. So after initiation of the cold leg brake, now you see there's a medium size, about 2,000 centimeters square. Kilogram per second. Or actually, this is the British units, pounds per second. You see the brake flow now. The primary pressure dropped rapidly from 2,000 psi to 1,000. Okay, and without the ECCS using pumps like all the conventional PWR, there's a passive residual heat removal system using a huge in-containment refueling water storage tank. That tank is a Nuna's shape inside containment and physically very high above. So the steam, the hot water in cold leg will naturally driven by the density difference. This condensate return valve, the return valve will open. So the hot water will go into the heat exchanger inside the pool, and cool down. This valve automatically open, return the water into the core. So there's no high pressure safety injection pump. And when the pressure is down to when the pressurizer level is going down, the coolant makeup tank will open. And they are physically also located higher than the core. So the water, once this valve automatically open, the coolant will be to make up the local loss. And the third layer of ECCS is the conventional accumulator. They are nitrogen-filled tanks with highly borated water, and this check valve open, the water will, so see 3, 1, 2, 3. This water will go back to the core. And here is the drain valve. Drain valve now is not open. Only when the pressure of the reactor become the same as the containment pressure. So just by gravity, this drain valve will open to replace the coolant loss. So this new concept cool the core to remove the decay heat. In the meantime, the containment is a passive containment cooling system. So we click to switch the display. You see the containment, the stainless steel liner, like an egg shape. So we have a loss coolant excellent here. The primary coolant go to the containment, primary containment. So the steel shell become very hot. The containment spray is actually spreading outside the liner from the tanks at the roof of the containment. The containment is built by reinforced concrete. So because the hot shell of this inner containment, air in the atmosphere will be sucked in, going downward and heated by the steel shell going upward, and just driven by the draft to remove the containment heat. And the valve will automatically open to spray water from the top, from the rooftop to the outside of the shell. So water will cool the steel shell and going down to the bottom of the floor of the containment. So this is the passive containment cooling system, unique for AP1000. So we keep track of the not only the pressure, temperature, the operating variable, but the radioisotope inventory. So the primary coolant, if there's no failed fuel, the fission product of the fuel will not be released. Only the iodine and noble gas may go into the containment, but containment is pretty solidly sealed. Nothing will go out. So you see the auxiliary building, the steam line, the turbine condenser building, and the offsite exclusive area boundary or low population zone. But those are minimal. Even you have a moderate size line break accident. But if we allow, for whatever reason, the containment have an open leak or an isolated valve, I just type in a random large number here, assuming there's a containment failure. Run it. You see, there's a small leak, and your outside dose will go up. So this gives you an idea what AP1000 is different from all the conventional PWR. And hope you get the idea. Okay, and the first AP1000 is now under hot function fuel loading in Xiamen plant of Zhejiang province of China. So soon you'll see the AP1000 Generation 3 power plant become a reality. Thank you. Bye.